Okay, we're still in chapter 3 on differentiation where we're learning about rules, and we're into sections 3.6 and 3.7 in these notes. Both of these employ a very important rule, really our last rule that we're going to talk about, called the chain rule. So first of all, let's try to understand the chain rule in general. Basically, the chain rule is for taking the derivative of a composition of functions, right? So if I have a situation where I have f of g of x. So this notation here is essentially what Newton did when he first invented calculus. And then down here we have similar, it's the same rule, it's just different notation. And this is what Leibniz used when he essentially invented calculus about the same time as Newton. Kind of a neat historical fact, but different notation. Okay, so the way this works is if I have a composition of functions, I take the derivative of the outside function, f prime, leaving the inside function alone, or think of it as still evaluating it at g of x, then I multiply that times g prime of x. Or in Leibniz's notation, if I think of y being f of u, where u is some g of x, right? So that's my composition still, f of g of x. It's just that I'm calling u g of x. Then to take the derivative, dy dx, I first of all take the derivative of y with respect to u, but then I multiply it times the derivative of u with respect to x. So you can kind of see if these were thought of as fractions, you could cancel this du and you would get dy dx. Again, that's just no different notation, but for the same thing. So this is a pictorial idea of what's going on. So let's go through this example and see how these two notations are the same thing. So here in example 43, I want to take the derivative of y equals 3x squared plus 1, quantity squared. All right, I want to find dy dx here. So I'm going to first use Leibniz's notation. So this is like y equals u squared. So u is my inside, right? U is 3x squared plus 1. So the first thing I think about if I want to take dy dx is I take the derivative of y with respect to u. So I think of y as being a function of u, even though it's really a function of x, right? So I think of it as being a function of u. So the derivative of y with respect to u is 2u. So there's my 2u. Then I multiply that times the derivative of u with respect to x. So the derivative of u with respect to x is 6x, right? This is a pretty simple derivative, 6x. But I can't leave it in that form. I have to put u back in terms of what it is because I need everything to have x's in it, no u's included. So that's 2 times u, but u is 3x squared plus 1 times 6x. So I could simplify a little bit, I guess. I could distribute all the way through, but I'll just multiply the 2 times 6x and get 12x times 3x squared plus 1. All right, so then if I think about it in terms of Newton's notation, the derivative with respect to x of a f of g of x, right? I have f of g of x. That's f prime of g of x times g prime of x. So in our case, what I have here, my f of x is x squared because f of g of x would mean take g, plug it in everywhere you see an x in f of x, right? So f of g of x would be 3x squared plus 1 quantity squared. So the way you think about that is you multiply it, you take f prime, now f prime is 2x, but I'm evaluating at g of x, so g of x goes in there for x, so it's 2 times the quantity, 3x squared plus 1, times 6x, and you can see that it's the same thing, 12x times 3x squared plus 1. So a lot of times, when I write this out, sometimes this notation can start to confuse people at first. This actually becomes a very easy rule to use, and students usually like it pretty quickly. It's just a matter of understanding it first time through. Think of it as the derivative of the outside evaluated at the inside times the derivative of the inside. Okay, or sometimes people say the derivative of the outside, leaving the inside alone, times the derivative of the outside. Times the derivative of the inside.